Zeal Education Society, redefining excellence.
Hello, good morning to everyone. I am Dr. Mahadev Unde, Professor, Zeal College of Engineering and Research, Pune. In a previous video lecture, we have learned the alternating current flowing through pure resistance. Its current equation, their phasor diagram, waveforms, and the power consumed. In this video lecture, we are going to learn alternating current flowing through pure inductive circuit. So AC through pure inductive circuit having inductance L. Consider the purely inductive coil as shown in the figure, and let the alternating voltage small v equal to V max sine omega t is applied across your inductance. So this is L, and the current flowing through is small I. The same current is coming out. The voltage drop across this is VL. So whenever AC voltage is applied to the inductance, the back EMF is induced in it because of the self-induced EMF. This self-induced EMF opposes to the every change in current flowing through the inductance. Now, as the circuit contains only purely inductance, the induced EMF equal to the supply voltage, and this self-induced EMF VL equal to L di by dt, and this is equal to phi means V max sine omega t. Therefore di equal to Vm divided by L sine omega t dt. Taking integration on both sides, integration with respect to t, Vm upon L is constant, sine omega t dt. So I equal to Vm upon omega L minus cos omega t. Therefore this can be written as I equal to V max upon XL sine of omega t minus pi by 2, where minus cos omega t equal to sine omega t minus pi by 2. Therefore I equal to I max sine omega t minus pi by 2. So this is the expression for current flowing through the inductance. Now comparing equation 1 and 2, it is observed that from equation 1 and 2, it is observed that current is lagging the voltage by pi by 2. Further, XL equal to omega L equal to 2 pi FL ohm is known as inductive reactance. Inductive reactance its unit is ohm, and it opposes to the flow of supply. Now here XL, from this equation, XL is directly proportional, XL equal to 2 pi FL, that is XL is directly proportional to L, directly proportional to F. Therefore, as the frequency, this is the frequency on x-axis and the inductive reactance XL on y-axis, it is a straight line relation. Okay. Now let us see the waveform. See, T or theta, and here it is voltage and currents. This is origin. Now the equation 1, when t equal to 0, the sinusoidal voltage is 0, and therefore it is a reference quantity. We can draw it like this. So this is the expression for voltage. Then draw the expression, the waveform for the current. The current waveform, here the current from equation 2, current is lagging the voltage by pi by 2. Therefore its waveform will be like this. This is for the current I. Now come to the phasor diagram. Now here let us take the voltage as a reference vector. When the voltage is considered as a reference vector, see, phi, then current is R. Remember that phasors are always represented by RMS values, and RMS values are denoted by capital letters. So this angle is 90 degree. And how to observe? Always observe in counterclockwise direction. Current is lagging the voltage by an angle pi by 2. R. This can be shown like this. Taking current as a reference phasor. See, this is the current I. The voltage will be here, phi. Here is also 90 degree, and observe the counterclockwise direction. So the angle phi equal to 90 degree, and therefore power factor equal to cos phi equal to cos of 90 degree equal to 0. Therefore P equal to phi I cos phi equal to 0. So conclusion. Pure inductance does not consume any power. Pure inductance does not consume power. Now let's have a power expression. See, from equation 1 and 2, P equal to small v into small I. Now what is small v? Phi max sine omega t. What is I? I equal to I max sine omega t minus pi by 2. Now this can be written as phi max I max sin omega t into cos omega t. Here it is a minus sign. So this can be written as phi max minus phi max I max upon 2 sin 2 omega t, because sin omega t into cos omega t equal to half sin 2 omega t. Therefore, the power expression has the double the frequency as that of the current and voltage, and its integration over a complete cycle, power over a complete cycle. So integration from 0 to 2 pi sin 2 omega t dt equal to 0, and therefore t equal to 0. Thus pure inductance does not consume any power. Okay. Now let us have a power waveform. Now see, from this point to this point, the voltage is positive and current is negative. Their product is more and it is negative. So this is the waveform for the. Now between this band to this band, both current and voltage are positive, their product is positive. So when the voltage completes one half cycle, the power waveform completes the one complete cycle. From this to this band, here current is positive but voltage is negative, and therefore their product is negative. In this band, both current and voltage are positive, and therefore their product is positive. So when the voltage completes one cycle, power waveform completes two cycles, P equal to small v into I. See, it has equal positive halves and equal negative halves, and therefore P average equal to 0. Equal positive half and equal negative half. Therefore P equal to 0. So in this way, the pure inductance does not consume any power. So in this video lecture, we have learned that whenever alternating voltage is applied across the pure inductance, it is opposed by the back EMF, that is known as self-induced EMF. This self-induced EMF takes place in any machine having the windings, and because of this self-induced EMF or reactance voltage, there is delay in commutations in the machines. When V equal to Vmax sin omega t is the supply voltage, then current I equal to I max sin omega t minus pi by 2 indicates that current lags behind the supply voltage by an angle pi by 2. Further, the reactance offered by the inductance is known as XL, and it is known as inductive reactance, and XL equal to omega L equal to 2 by FL, and its unit is ohm. So XL is directly proportional to the frequency, and therefore it has a straight line relation. It has a straight line relation. As the frequency increases, the inductive reactance increases. Then we have seen the waveform, from the voltage as the reference vector. When t equal to 0, voltage is 0. However, when t equal to 0, the current is not 0, t equal to 0 sin minus pi by 2, it has a negative value, but it has a certain definite value. It has certain definite value which is here. Okay, and so the waveform we have shown. Then we have seen the phasor diagram. When voltage as a reference vector, current lags behind the voltage by pi by 2, or by considering current as a reference phasor, the current is lagging the voltage by pi by 2. The angle between voltage and current is 90 degree, and therefore power factor equal to cos phi equal to cos 90 equal to 0. We know that power P equal to Vi cos phi, and therefore power equal to 0. So the conclusion is this: the pure inductance does not consume any power. We have also obtained the expression for power, that is P equal to 0, and the power waveform has double the frequency to that of the voltage and current. So friends, we will stop here. Thank you.